Hi, today I will talk about the V2X and its technical challenges, some solutions to these challenges, and some open problems for the future work. The first part is a brief introduction of V2X. In recent years, V2X communications gained huge interest because it can reduce traffic jams and enable autonomous driving. Basically, V2X means vehicle to everything. This figure illustrates some commonly identified forms of intelligent transportation systems, including vehicle to vehicle, vehicle to infrastructure, and vehicle to network, collectively referred to as vehicle to everything. Then I will describe some important communication standards for V2X. The first one is DSRC. The DSRC has wide-range applications in V2X communication, and mainly in areas related to safety. It originated from IEEE 802.x family, and it utilizes the 5.9 GHz licensed spectrum and consists of 7 channels. Each of the 7 channels have a bandwidth of 10 MHz. Despite the use of DSRC in V2X, it faces certain limitations. The poor performance of DSRC arises due to the chance of high collision, especially in situations have excessive density of vehicles. Therefore, for applications that are delay sensitive, DSRC is not a good choice for them. The second one is Wave. This architecture is developed on IEEE 802.11 standard. It supports both IP and non-IP applications. The architecture of Wave is made up two stacks, having common layers between them. The next one is LTE. The advantages of LTE-based V2X are that it provides greater mobility, higher network capacity, and greater coverage when compared with 802.11p, but has a disadvantage of higher latency, and there's an increased network load. And the last one is 5G V2X. The 5G systems have features of being highly flexible, together with programmable end-to-end communication, computing infrastructures, and networking. All these features lead to enhanced performance with reference to throughput, reliability, mobility, latency, as well as satisfying the diverse requirements from many services. There is a table comparing these communication standards from the bitrate, coverage, latency, and many other aspects. From the table, we can see that 5G has the highest bitrate and bandwidth and the least theoretical latency, but a relatively short coverage. It needs more subcarriers, and we may need to build more 5G base stations to provide the service. The V2X consists of many applications, such as traffic management applications, which helps drivers with the information about the potential dangers and the situation that are not visible to them. The primary challenge in these safety applications lies in achieving the low latency, and also in road safety applications, which helps drivers know the local traffic information. Vehicles receiving messages related to traffic management should adapt necessary actions, such as avoiding the underlying hazard. In this part, I will discuss the challenges for V2X. The first challenge is latency. Latency is one of the essential challenges of V2X because the management and control network connections among vehicles, between vehicles, and network infrastructures are the most crucial issue of the vehicle network's communication. The primary challenge in vehicle communication is to provide an acceptable delay performance under the constraints of network throughput and channel bandwidth. High latency will cause a high delay in network response. Consequently, vehicles will receive response too late, preventing the function of real-time applications. Latency in V2X communication may result certain issues, such as which information to collect and what to filter, which data should be processed, and what should be transmitted and received. Therefore, all the factors that relate to communication latency in V2X should be addressed so that safety and security situations are handled in real time. In my opinion, we can think of V2X service as collision avoidance. For example, if there is high latency in network connection, the response of the collision avoidance service may not arrive on time to avoid a collision with another. Of course, it depends on the drivers too, but if there is little delay, the chance of not having a collision are higher. As mentioned before, 5G has a low latency compared with other V2X communication standards. The application of 5G network can help V2X obtain a low latency. The second main problem is bandwidth. It is related to the latency. Usually, a network that has a high latency also has a low bandwidth. I think it's because of the unavoidable hardware constraints. Actually, the network environment of V2X has unreliable, shared, and limited bandwidth. This is a severe challenge because in order to satisfy its application's requirements, one needs to guarantee efficient and reliable delivery of data packets to all vehicles and infrastructures inside the coverage zone. As in the case of latency challenge, bandwidth problem could be also solved by means of 5G as increased bandwidth, for example, up to 10 gigabit per second, is one of the promise of the next generation infrastructure. Another issue that needs to be considered is the security challenge, because it's essential to avoid devastating consequences of potential attacks and vulnerabilities. Because of the high mobility and big scale of V2X network, it's not easy to guarantee data confidentiality and integrity. The privacy of each driver must be protected, and the messages need to be encrypted to prevent outsiders from stealing the driver's personal information. It's important to emphasize that data reliability is not only a security issue, but a connectivity issue too. If there is no reliability of network connection, the data exchanged could be corrupted in the middle of the communication. This could happen even if it's not suffering a malicious attack, such as denial of service. Strategies involving 5G connection could be adopted to solve this issue. The technology of 5G networks offers a higher level of security, privacy, and quality of service. Meanwhile, we need to consider the data priority. The V2X communication network should be able to prioritize data received from hundreds of nodes. The data processing should be taken into account buffering and queuing techniques for ensuring an efficient data communication link. The data received from security critical sectors must be handled with the highest importance so as to prevent potential damage in the network. Actually, users' trust and privacy is also a challenge. In the V2X system, ensuring the user's trust is a major challenge to overcome. It's very much true that customers do not desire vehicles susceptible to privacy issues or traffic rules violation. Effective measures for protecting users' privacy are by using cooperative intelligent transport system. Other techniques are by using group-based solutions or by decentralizing the key distribution process. Also, there are other techniques that depend on group signatures, where vehicles in close proximity are grouped together. So in grouping, only one signature is generated, resulting in protection of the privacy of the group members. In my opinion, for the actual scenario, the proposed solution may not be good enough, and therefore we may need some hybrid techniques. In this part, we will talk about the current solutions to mentioned challenges. First, Let me introduce an architecture proposed by Srinivasa and his team to minimize the latency for 5G V2X application using mobile edge computing. We'll call it MEC. This suggests that MEC sites are interconnect directly and enable communication over XN interface. Through the XN interface, the inter-MEC exchange control and barrier traffic is enabled in less delay as compared to a central architecture. So basically, in the first step, user equipment creates the content and share it with the nearest GNB, which is a logical 5G radio node. It hosts the session management function. In step 2, MEC detects the content is fresh or newly generated. In the next step, the content is propagated to the 5G core by updating. In step 4, application server queries the information of participating MEC site information from the MEC pushing strategy model. In the next step, the push strategy updates the GNB site information to the application server hosts the content. Then the 5G core site pushes the content to the participating GNB sites, have an MEC function. In the last step, the content is sent to the participants of the group. In this case, is a car and the mobile terminal. It will use the unicast and multicast strategy. The following algorithm is used for V2X application to obtain the low latency information. Basically, V2X will initiate a request as a GNB along the drive path. As the vehicle moves, additional delay is introduced due to the extra hop to fetch the content from the original GNB where it was connected. They use some equations to calculate related values and update the total download rate. This figure shows the latency for the V2X application. The x-axis presents the number of GNBs, and the y-axis presents the time taken to download content in milliseconds. This plot shows the latency value with age SYNC, without age SYNC, and the overall latency. It can be noted from the figure that if the contents are placed at GNB close to the vehicle, there is a significant reduction in latency, as shown by the line latency with HSYNC in my graph. Then I will introduce a method by Xi and his colleague to handle the privacy-preserving authentication issue in V2X. It is achieved by using symmetric random key sets. In this work, all the valid keys form a key pool, and each member will randomly draw a key set from the key pool. If the size of key pool and the size of keys held in each member are properly chosen, there is a high probability that one key is shared by a set of members. Authors actually take advantage of these features. The system architecture is shown in this figure. It consists of key distribution center or KDC, service providers, vehicle registration sites, RSU for roadside unit, and OBU for onboard unit. A KDC serves as the central authority for administrating keys and identifying an attacker. RSUs actually authenticate vehicles, and OBUs initialize authentications on behalf of users. Authors actually give some mathematical explanation about their model. They denote that N as the total number of the keys in the key pool, K as the total number of keys in one vehicle, A as the number of keys that are sent for authentication. So this probability means that given A keys, the probability of another vehicle sharing at least those A keys. This is also directly related with the probability which RSU can identify an attacker. So in this figure, we only show the probability for different values of A. It can be seen that the probability decreases sharply with the number of shared keys increases. This is a good property for identifying an attacker from its intermediate neighborhood. So the details of privacy-preserving protocol is shown in this figure. First, the RSU announced its service by broadcasting certificate signed by the KDC. So when a vehicle decides to access the service, it will send an authentication request together with a set of key indices. So key set consists of a set of symmetric keys shared by the vehicle and the RSU. A time information T1 is used for message refreshness. All this information is encrypted by a session key S. The session key S is encrypted with RSU's public key. This encryption protects the message integrity and prevents the keys from being disclosed to an outside observer. After the RSU gets the authentication request from the vehicle, it creates a challenge message by encrypting a random secret with a set of keys. Upon receiving the challenge, the vehicle decrypts the challenge with the chosen keys and creates a response by encrypting the random secret with a session key. So upon the successful verification, the RSU accepts the session key and the vehicle is authenticated. So in this section, we present some open problems and future research directions. One is a secure network caching at network edge. So caching the frequently requested data at storage spaces on the edge devices is an effective and efficient way to reduce the latency of V2X services. However, it's hard to ensure the confidentiality of the cached data, so from which the attackers can infer the interest services of a target vehicle. Another is a secure driving for autonomous vehicles to guarantee safe autonomous driving. So every key procedure should be protected against hackers, including the data collection, data exchange, data analysis, and decision making. Currently, the secure 5G V2X communications only provides the reliability of data collection and data exchange, but it can't ensure decision correctness and control security. So it's very important to make an autonomous vehicle drive safely. So that's all my presentation. Thank you for watching.